Hi, today we will be learning the tangent and velocity problems in calculus. The following book is what I'm using as reference. James Stewart, Calculus 8th Edition, Early Transcendentals. First, let us address the tangent problem. The word tangent is derived from the Latin word tangens, which means touching. Thus, a tangent to a curve is a line that touches the curve. A tangent line should have the same direction as the curve at the point of contact. And so here's some examples here. Here's a tangent line. The purple line is a tangent line. And it's touching the curve. This is a curve. And it's going the same direction. So if you guys don't understand what I'm trying to show you, I'll show you what I mean. So we have a line. And there's a little point right here. And there's a line touching that point. Just at that point, specific point, let's make it even closer. So we got a big old line right here. We got this dot. And this purple line right here is called a tangent line, right? It's touching right there. It's going in the same direction, because where is this going? What direction is that going? It's going up. This is going the same direction up. This direction is going down. It's going the same direction. Alright, and so what's the problem with these ones? They're not going the same direction. So these examples are not tangent lines. And so let me use this parabola for an example. So we have a parabola, and we got a point. So this is our point. In order for this to be a tangent line, it needs to go the same direction. And so in order to go the same direction, we need to go like this, straight. Because if you zoom in closer, so this is super close, right? It needs to touch the given point, so this is our point, and it needs to go the same direction. And this is not going the same direction. That direction is going, it's going up, and it's going down. You understand what I'm saying? So that's what we need to know about tangent lines. Because of the way tangent line to a curve is defined, the tangent line to a straight line at any/every point on the line is the straight line. And so let's look at this example right here, or diagram, my bad. So in this diagram, we're given a straight line, and the tangent line is within here. So let's say this is our tangent line. So that's our tangent line, and this blue line is just a linear line. So linear. And our tangent line is touching every single point within our linear line. And so I'm not going to go prove this, but I'm just wanting to show you this is a tangent line, and it's touching every single point. Likewise, when I show you the parabola, it's going to be touching the curve. So a line's a curve, if you guys didn't know. And I'll just show this one more time, so we could kind of put it in our heads. So it's a point of interest, and here's our parabola, and it's me touching, just touching, not all over it. Now, with the tangent lines can touch multiple parts of the curve. So if we were to look at our example for this past, if we were to look at the example that I just showed you, right, the one where it looked like this, it would have 2 points on it. Now, what's happening is this is our tangent line. It has the same direction, right? The direction's left to right, so it has the same direction. Is that these 2 points have the same tangent line, just at 2 different points of interest. So 2 tangent lines, the same thing, just 2 different points of interest. And it's touching the curve, and it's touching twice, but it's the same tangent line, just 2 different points of interest. And it still follows the definition where it's touching the curve and it is going the same direction as the curve. A secant line, from the Latin word secans, means cutting, is a line that intersects a curve more than once. And in this example, we'll be using a parabola. So we have a parabola right here. We got 2 different separate points, P and Q. And we have our secant line touching these 2 points in our curve. And so what's happening is we got these 2 points and we have this line cutting in our curve. So let me show you another example. So we have something that looks like this. Alright, so let's say we want to look at these 2 points. Let's say this over here. Then we're going to have a line that's going to be touching both those points. Let me see. So we have a line like this, touching both these points. So that's a secant line. It's going to be touching 2 points of interest. For our given curve. So this is really important, and we're going to go over it right now. Example: find an equation of the tangent line to the parabola y equals x squared at the point P11. Alright, so we're given our point P11. We also need to find another point, and we're going to call that point Q. So it's going to be an arbitrary point. So arbitrary means doesn't really matter where it's at. So let's put it right here. So then call it point Q. Right? And so we're given our point P with an x value of 1 and a y value of 1. We need to find what values these are, x and y. So what we know about this problem, we know that y equals x squared. So since we know y equals x squared, we know what the y is. So it's going to be x squared. So that's our arbitrary point, and its position on the parabola. So Q is x squared and P is 1, 1. Let's find the slope of the secant line. We choose x is not equal to 1 so that Q is not equal to P. Then MPQ, which means the slope of P and Q equals x squared minus 1 divided by x minus 1. So what this sign means, it means it's not equal to. And we're trying to find the rise over the run. And so earlier we're given our points P and Q. P was 1, 1. And Q was x and x squared. And so we're given these 2 points. And we're going to do the rise over the run. And so what would that look like? It would be x squared minus 1, x minus 1. Because this is x and this is y, right? So pretty basic. Now we need a number close to x1 yet is not equal to x1. How would we do that? So in order for us to do that, we need to plug in numbers in order to get a approximation of what the slope of the tangent line at the point P11 is. And so our equation was x squared minus 1 over x over 1 minus 1. And so we need to plug in points close to 1, but not 1, because what happens when we put 1 in here? It's 1 squared minus 1, 1 minus 1, which is 0. So we already know this is undefined, but let's say up here, 1 minus 1, undefined. So we know what this equals to if it's 1. And we don't want that. So we need to put it in numbers close to 1. And so I'm going to write out some numbers. So here we have 2. And 2 equals 3 of our slope. So we put 2 in here, which would be 4 minus 1, which is 3. 2 minus 1, which is 1. That's 3 over 1, which gives us 3. If you guys want to work it out, you guys could work it out. I'm just going to put these points out right here. It's pretty simple, so simple math. So I mean, if you're taking calculus, you should kind of already know this, how to do that kind of math over there. So that, as we can see right here, it's getting close to 2. Now let's see over here. If it's 0, what happens when we put 0 in here? Well, 0 times 0 is 0, minus 1, 0 minus 1, that's 1. So, you know that's 1. And when it's getting closer to the number 1, which we can't have it number 1, remember? We said x cannot equal number 1. It's going to be 1.9. 0.99. It's going to be 1.99. And just to be sure, we're going to do it one more time. We do 0.999. We do it with this kind of numbers. You might just want to put it in a calculator, because it's going to be some big numbers. Not saying that you should use a calculator all the time. And so the closer q is to p, the closer x is to 1. And it appears from the tables, the closer mpq is to 2. So in other words, the closer, I'm going to show us our graph again. So we have these 2 points called q and p. Oh, my bad. It's the other way around. PQ. And it's saying when this point's getting closer and closer to P, so let's say it's getting closer, it's getting closer, it's getting closer to 2, the number 2. So, what does MPQ stand for? MPQ stands for the slope of the secant line. So slope of secant line. And I want you to understand that this is MPQ is the slope of the secant line. So, but we're trying to approximate the tangent line, which is 2, right? So, two different things. We're two different lines. So this is the tangent line. This is the secant line. This is the secant line. All these little points are the secant lines. But once it hits the number 2, which would, when the numbers converge together, it's going to be the tangent line. So two different separate lines. And remember what I said, the secant line is this little line that goes through Q and P. But when this gets closer and closer, which what we wanted it to do, when it gets closer and closer, it's going to have a graph that looks like this. I mean, a curve that looks like this with the little line that's going touching it, not touching two separate points right here. So just keep that in mind. We say the slope of the tangent line is the limit of the slopes of the secant lines, and we express that symbolically by writing limit QP, the slope of MPQ equals M, and this is just the general form. And here's our example. Limit x to 1, x squared minus 1 divided by x minus 1, and it converges at the number 2. So that's our example. And like earlier, I'm going to show you one more time. We have this line, we have a parabola, and we got these 2 points, Q and P and Q, my bad. And they're going to get closer and closer to P. And why is that? Because we're trying to find the tangent line for this given point. And if we were trying to find the tangent line for this point, which this is an arbitrary point, we can't find it anyways. Or we can, we'll just be tangent lines everywhere. But we're trying to find the tangent line of P. So it's getting closer. Let me use a different color. Closer, closer, and I didn't say this earlier, but the tangent line could come from the left or the right, like how we had the diagrams with the different numbers of 0.9 and 1.1 whatever. So it could go from the left and right. So it all comes and converges at the point of interest, which is P. Use the point slope form of the equation of a line y minus y of the indices 1 equals m x minus x of the indices 1 to write the equation of the tangent line through 1, 1 as. So here's our answer. So we know our slope, which is MPQ, but this means secant, so we need to have the limit of this, which would be Q and P, my bad. Q and P. So I'm just going to put the general form. So we know our tangent slope, and which is 2. So now we just need to put it in here, and we know this. So if you take in algebra, you know what to do. And we had our point, which is point P, 1, 1. We just put it in, plug everything in. So let's see. The minus 1. And when I was saying indices, there's the little numbers right here. These are our indices. Indexes. Indices means multiple. Index means 1. So we got that. Oops. I was talking and not thinking. So that'll be 2 x minus 1. And so let's simplify that. That's y equals, let's see, 2x minus 2. That I forgot to distribute. Skip the step. That's why I tell you never skip a step. So 2x minus 1, because we have to add these. So you guys could probably solve this by yourself anyways. Everything was already given. So that's our answer. And so thus we found the equation of the tangent line. So this is our equation of the tangent line. And 2 is our slope of the tangent line. And the secant of our tangent line was all these little points. So that's 3 things to remember. So this is our equation of the tangent line. This is our slope of the tangent line, and all these little points of interest over here when we go and have these lines, that's the secant. line, right? So the velocity problem. If you watch the speedometer of a car as you travel in city traffic, you see that the speed doesn't stay the same for very long. That is, the velocity of the car is not constant. We assume for watching the speedometer that the car has a definite velocity at each moment. But how is the instantaneous velocity defined? Let's look at this example of a falling ball. And so, instantaneous velocity. I want you to remember that. Really important. And for whoever doesn't know what a speedometer is, I don't know, some people don't. It's this little gauge where it shows you how fast you're going. It has a bad drawing. Let's see. Has a little gauge, has a little arrow pointing, and it's showing how fast the car is going. So this is just my drawing. So it's 60 miles, it's 120. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. And we need a little background first. Through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. This model for free falling neglects air resistance. If the distance fallen after t seconds is denoted by st, which is right here, st, that's our function, and measured in meters, then Galileo's law is expressed by this equation. St, which is our function of 4.9 t squared, and y, this is half of acceleration due to gravity, a natural law, so this is given. If just in case you want to know where this number is coming from. Gravity 9.8, and this is just half of that. Acceleration. This is acceleration. Acceleration due to gravity, yeah, and this is what's happening when the ball is going down. A lot of people haven't taken physics. I didn't take physics. The difficulty in finding the velocity after 5 seconds is that we are dealing with a single instant of time, t equals 5. So no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second from t equals 5 to t equals 5.1. And so this would be expressed by average velocity equals change in position divided by time elapsed. And so our time elapsed would be 0.1 because 5.1 minus 5 is 0.01, and it already said 1/10 of a second. And our given function, which is s of t, right? So that's why this is expressed this way. Change in position minus the change of position right here. So our given position was 5 seconds, because that's what the question was asking. The question is saying, and read the question again. It says, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. So what's happening after 5 seconds? So this is 5 seconds, this is after 5 seconds. And so we plug in our function, which is, what's our function? S of t equals 4.9 t squared. So 4.9 times 5.1 squared minus 4.9 times 5 squared. And this gives us 49.49 meters squared. And I want to show you what's happening. So we're up this tall building. a building doesn't look like this, and we throw something off, or it says drop, so there's no force behind it, we just drop it, and it's gonna go down like this. And I don't know how fast or how long it will take to hit the ground, but I know that, what do you call it, at a given time it's going to be somewhere around here. So let's say right here it's 5 seconds. We're trying to find, I can't even spell, let's see, back, okay, 5 seconds. So this is 5 seconds, and we're trying to find what's the velocity of the ball after 5 seconds. So that's why we're using this time interval of 5.1. So right here, average velocity over successfully smaller time periods. So we're going to be given our time period intervals between 5 to 6, and so our average velocity between here be 53.9, because we're plugging in our number for 6, like the function we had earlier. And so right here we have a time interval of 5 to 5.1, and we end up getting the number we had earlier. And so we're trying to approximate the closest number to 5. And so this is really close to 5. Just 1, my bad. 1. Let me go back. 1. There you go. And it's going to be 49, because you could clearly see that it's getting closer and closer to 49, so it converges to 49. And what's happening is, like what we did last time, remember? We had this parabola, and then we have these given points. We're trying to find our secant line to get closer and closer to, which won't look like this, it will look like this. We're trying to get closer and closer to this arbitrary point P, which would be 5, which is an arbitrary be 5. So the instantaneous velocity t equals 5 is defined to be the limiting value. So limits, this is what we're doing right now, of their average velocities over shorter and shorter time periods that start at t equals 5. Thus, it appears that the instantaneous velocity after 5 seconds is v equals 49 meters per second. You may have the feeling that the calculations used in solving this problem are very similar to those used earlier in this video. To find tangents, in fact, there is a close connection between the tangent problem and the velocity problem. If you draw the graph of the distance function of the ball, if we draw the graph of the distance function of the ball and we consider the point P, a, 4.98 squared, and Q, a plus h, 4.9 a plus h squared on the graph, then the slope of the secant line PQ is, so this is the slope of the secant line, and PQ, remember, equals 4.9 a plus h squared minus 4.9 a squared, a plus h minus a. So this just looks like a bunch of numbers right now, but I'll explain it right now. So remember what the slope is rise over run. And so this is our given graph. But remember the function is s equals 4.9 t squared. S equals t, remember? Our x is t. And so these are 2 points, P and Q. We denote P as A, so this is our initial point. So right here, that's A, right? Right there is A. A is our initial point. we make a equals t. So we say let a equals t, or t equals a in this point. But if we want to change it back, we say let a equals t, and this all turns into time, because this is what this is, right? That's our time interval. And this is our acceleration. So p right here, that's our a, and everything after our a is h. So a plus h, so everything going forward, that's h. So that's why we have this right here, a plus h minus a. So remember what's happening, we're doing the rise over the run. So a plus h minus a. So that's going to be in the bottom because these are our x's. These are our y's. And it's q minus p. Q minus p. That's why we have this on top. So just wanted to show you that. So what's happening is the same as the time interval a plus a h. Remember what I said? That's our time interval. Therefore, the velocity at time t equals a. The limit of these average velocities as h approaches 0. So as h goes to a, it's approaching 0. H is approaching 0. Must be equal to the slope of the tangent line at p, the limit of the slopes of the secant line. And so this is shown over here. As q gets closer to p, remember what I showed you earlier, so don't get all confused because there are all these variables. And as h gets closer to a, where you end up with the tangent line. And this is just what the equation is saying. This is a beautiful equation because it's simply stating how we're getting to the tangent line from our secant line. So this is our secant line, and we could have any number right here. Honestly, this could have said x. It's just saying that we are getting closer and closer to p. Now if this was x, if this was a different given function, then these things would change, right? The exponents and everything. But like I was saying, so you don't have to worry about how complex this looks like. It's really simple. 0 is going to a, q is going to p, and this is basically saying this is the secant line. This is basically trying to tell us there are limits approaching p. Our limits going to p. And it would say limit q is approaching p. So limit q is approaching p, like earlier in the video. So I want you to take note of this. In order to solve the tangent and velocity problems, we must be able to find the limits, and limits are really important, and we'll learn about that in the next couple of chapters. If you like and enjoyed the video, please leave a comment down below and like and subscribe to the channel. It would mean a lot, and I really enjoy making this content. So if you have any suggestions, please let me know, and I can't wait to see you guys all next time. Thank you, and goodbye.